Ready? Okay. Welcome back. Okay, I'm glad I'm saying that the number of students rise. Continue this level. By the end of the semester, we'll have a full class here. Okay. So, recap. Ask me about my lecture notes. My lecture notes are my lecture notes. If you need something, go to the books. We'll post them once we finish this chapter, then I'll put them in the course info page. But really, I did not invent any of them myself. So all find it in the textbooks. Go there, read it. Have your own lecture notes. They will be available to you at the end of the next week, I guess. We spoke about vectors. We just started about that. We have many discussions about vectors. After I defined, so let's go even backward, right? So I defined a Lorentz transformation as a what? So the Lorentz transformation is any transformation from one coordinate system to another coordinate system that conserves the interval. Right? So the interval, which I define delta S, or interval between two events. We have events. In special relativity, we speak about events. Interval between two events is defined as sum over mu equals 0 to 3 of eta mu nu delta x mu delta x nu, where eta mu nu is the matrix, which is known as the metric. Eta mu nu is equal to minus 1 plus 1 plus 1 plus 1 0 0 0 0 0 0 0 0. X mu is defined as CT x1, x0, x1, x2, and x3. Coordinates of notation. And then we said that the Lorentz transformation is any transformation between two coordinates O and O prime that conserves the interval, namely x prime. I wrote it as matrix lambda mu prime nu x. That's a Lorentz transformation, which has to fulfill certain conditions. Any transformation that conserves the interval. And then I moved on, not like this either. And we discussed about time dilation. I showed you what we get is exactly that you're familiar with. And then I defined a 4-vector. To be more precise, it's called a contravariant 4-vector. As any quantity whose components undergo the transformation V alpha prime, V alpha goes to V alpha prime, which is lambda alpha prime beta, V beta. Any quantity whose components transform as that when the coordinates transform. X alpha goes to x alpha prime, which is lambda alpha prime beta x. We will talk about various four vectors. Velocity, momentum, several. Acceleration, several. But in general, any quantity whose components transform like that, when the coordinates transform, like the coordinates, is called a contravariant form. And I said several things here. What happens to the vector itself, not its components, right? The component is just the way we describe the vector. What happens to the vector itself? Nothing. The vector itself doesn't care about how we specify it. That's something which is crucial, because the physics doesn't care about how we describe it. When something happens, it doesn't care the way we choose to describe it. That's a fundamental thing. Right? That's one thing. So the vector itself is unchanged. Nothing happened to the vector, just the way we describe the vector. That's one thing. Second thing I mentioned, vectors belong to a point. They do not connect two points, as you might be thinking wrongly. When you say we plot a vector like that, so some people might think that the vector connects point A to point B. No.
That's the way how mathematics define vectors. But in physics, no.
This is a mathematical definition.
No, I mean by 2 points. No?
It's just a way of illustrating something. The vector is defined at a point. And I mentioned right now, you don't see that when we look at Euclidean spaces, but there are many things you don't see when you look at Euclidean space. But think of a curved space. Think of the surface of the Earth, right? Earth is a sphere. Think of the surface of the Earth as a space. But in general, I said, I did not yet define it, and we will define it properly, don't worry. But I said, just think of any surface. And the only thing I can tell about the surface right now is that it is not a Euclidean surface globally. So think of the Earth as a sphere. It is not Euclidean. Namely, you cannot draw a map, 2D map, from the surface of the Earth to Euclidean space. That's a problem of cartographers. Right? When you draw a map of Earth, you always end up with at least one point which you cannot map. Typically, it's 2 points which you put in the north and south poles. That's why Antarctica looks so big. It's not really that big, just where we map it, right? So think of a surface, right? And then, but locally, so globally it is not Euclidean, but locally it is at every point. That's called a manifold. Okay? Just told you everything you need to know about manifolds. And I select a point P, and the vector on that manifold. And the vectors, all of them belong to that point, P. Okay? And the set of all vectors that go through this point P form a vectorial space, which we call the tangent space, T. It's a tangent space to the manifold at P. Again, the easiest way. Think of the surface of the Earth. With a piece of paper or cartoon, touch it like that. Which means that if you're going to a different point, Q, or a manifold, it has its own vectorial space, PQ. And they're not the same. It's going to be an interesting question, how we're going to connect vectors in P and vectors in Q. Right now, don't worry about it. Okay? So, set of all vectors, so vectors belong to a point. Okay, that's a crucial thing. The set of all vectors that go through the point forms a vector space. The set of all vectors that belong to a point P form a vectorial space, which we call TP. Of course, it's space-time. And it has all the properties you're familiar with from linear algebra. I was surprised last time that you said you didn't know about the dual spaces. Yes, vectorial spaces is the first thing you do in the first lesson in linear algebra. So that I assume you all know. If this is a wrong assumption, I should better know about it. No, you should tell me. Right? So that's called the vector space, which we call T. And then, we looked at the basis of this vectorial space. So there are infinite number of bases. We choose whichever vectorial basis we want. They all contain the same number of vectors. Right? We choose the dimension of space. Right? And all the properties from a basis for a vectorial space, we have two properties. They need to span the space. Namely, every vector should be able to write it as a linear sum of the basis vectors, and it should be independent. Namely, there should not be any vector in the basis, in the set of basis vectors that can be written as a linear sum of the other basis vectors. I'm not saying anything new to you, right? So if I select the basis vector, which call it E U, this is a set of basis vectors. Then we could write down any vector A. A is written as A is some mu 0 to 3 in our case of A mu E mu. This A mu is the component of A. Yeah. And then I gave you like one example saying, okay, so I have a curve. So I can select the vector by setting the coordinates, write down the vectors v mu is the x mu over the lambda, where lambda is some parameter along the curve. Lambda equal to 1, lambda equal to 2, lambda equal to 3, etc. Okay. And then I asked, okay, what is the transformation law of the set of basis vectors? And we ended up that this transformation law of the set of basis vectors is not the same as the transformation law of the vector components, but is inverse. It's an inverse Lorentz transformation, which is also a Lorentz transformation by itself. If you go from frame O to frame O prime, then you can go back from frame O prime to O. Inverse transformation, it's still a Lorentz transformation. So we denoted it as the inverse transformation with the same lambda but with opposite indices. So first lower and then upper. So then we wrote down that lambda minus 1 of u prime u we wrote as lambda. Remember, there is this space, so not one on top of the other. Then you could write down that in the new basis, the new basis can be written as the new basis can be written as E. Mu prime is lambda mu prime mu in phi. And then I made another jump and I told you, okay, so I can think of other objects that undergo the same transformation as the basis vectors. Okay? They don't have to be no basis vectors. There could be other independent objects undergo a similar transformation, namely the inverse transformation. Right? And these ones dual vectors. And I define dual vectors. That is the thing that I was surprised if you did not see. You've seen it. Or admit that you've seen it. So, objects that transform like a set of basis vectors are known as dual vectors. And they transform and they form a vectorial space of their own, which is known as the dual space. Dual space TP denoted by TP star. And if omega is such an object that belongs to TP star, it means that it can operate on any object within TP to form a real number. And that is done in a linear way. So omega AB plus BW V and W belongs to TP is equal to A omega that acts on V plus B omega that acts on W, which is a real number. And the same A omega plus B eta works on V, operate on V. Omega and eta belongs to TP star equal to A omega that acts on V plus B eta that acts on V, and that also belongs to R. And basically, what we showed then is that we don't really need to write the full components, because omega operates on V. If we have the coordinates, then we know what are the bases. Of course, the basis to omegas to TP star is called the dual basis. And we said that omega operate on V, we can write as omega mu V mu, which belongs to R. Then we can define V that acts at omega exactly like that as omega that acts on V. So that also belongs to R. Which is essentially saying that the dual to the dual is the vector space itself. Okay, everybody's with me? Of course, what's the transformation law of the dual vectors?
The inverse Lorentz.
Of course, this is the inverse Lorentz. Omega mu prime is lambda mu prime nu omega nu. Transformation law of dual vectors. One, you should have seen that in linear algebra. Second, it's not your fault if you did not see it. But you did see it, you might not have called it that. So one happened to my examples. So one example with you, two examples that you've seen. Typically, when we speak about vectors or contravariant vectors, it will be noted as color vectors. So V can write it v1, v2, vn. Same way as I wrote the x meters, right? And then what will be the omegas? With the row vectors. So omega would be written as omega 1, omega 2, omega n. And the operation of omega on v
Inner product.
what?
Inner product.
It's exactly what you're familiar with from multiplying a row vector with the column vectors. So I don't know, how well your linear algebra understanding is, right? But you understand it's very basic, right? That V's and omegas, they live in different worlds, right? You cannot add V and omega, right? It's meaningless because they don't live in the same space, right? But you can operate omega on V. That is something which you can do, and I guess you did that in your linear algebra courses. Okay, so just have that in mind. They just live in different worlds. But somehow they can talk to each other, but they cannot add them or subtract. Another example, which I also mentioned, is familiar from quantum mechanics. Right? When we speak about the cats in quantum mechanics, what is a cat? Really? Maybe not like quantum mechanics cat. Psi. What is that? It's not a vector.
It's a wave.
Object. It's not even a wave. What is that?
It's a function. It's like an infinite vector.
Object of
It's an
over
object.
space.
I prefer to look at it as an object, which belongs to a space which we call Hilbert space, right?
Yeah.
Now, it represents a wave function, right? But it belongs to a vector, and it has a certain structure with this space. And
Hilbert space is not a vector space.
it is a vector space, of course.
So why it's not a vector?
It is a vector in Hilbert space, yes.
Ah,
Of course it is.
okay.
But I prefer to think of it as an object in a way, because it does some things. Something happened here. And then I can think of a bra, phi. That's a different object, which lives in a different space, the dual space. Right? And when phi is acting on psi, then we get a complex number. This is a C number. It's the same idea, basically. The last thing, which I think somebody mentioned, I think I didn't have time to talk about it last time, the gradient. What is the gradient of a function? I have a function phi. Okay. This is a scale of a scalar function. I have a scalar function phi, which is defined in the Lorentz space, such as the height of place above sea level. It's defined everywhere in the surface of the Earth. So the gradient is denoted by d phi. Okay. What is that? What is d phi? How do you define the gradient of a function?
It's a vector that points in the
It's a set of partial derivatives. So what is that? It's d phi over dx. You can write mu, doesn't matter. Delta d. So what type of object is that?
It's a vector.
It's a dual vector, which is also known as a covector. Dual vectors dual vector, also called covariant vector, also covector. They're all the same name. What I call vector and contravariant vector is also the same name, so I might switch to vector, contravariant. It also has the same name. So I can use the chain rule, for example, right? So when I change coordinates, right, I use the chain rule, so d phi over dx mu prime, I can write as dx mu over dx mu prime, d phi over dx mu, right? Just when you use the chain rule. So what is dx mu over dx mu prime? Change the coordinates from O to O prime. Okay? This is the old coordinate in terms of the new coordinate. So this is the inverse Lorentz transformation. This is lambda mu prime mu d phi over dx mu. So how does it transform?
By the inverse.
The inverse, which means that it's a covector. It's a dual vector. So conclusion is that gradient is a covector. Now you don't see that in Euclidean space. Why not?
Don't use a Lorentz transformation.
Because in Euclidean space, right, three-dimensional space, right, the metric, how does the metric look like?
Identity.
Just identity metrics, right? So vectors and covectors look exactly the same. Now because of that, we have a new notation, which we'll get used to. Because it's a covector, then I write the gradient in simple, in a quicker form. So notation for gradient d phi over dx mu. I will write it either as d mu phi. So mu here is a natural index. Right, so mu here will be lower. So this is d mu phi, that means d phi over dx mu. There is also a even simpler way. Phi, comma, mu. That's what it means. When you see that, you don't have that long to get used to that, because shortly that's going to be changed into an even more complicated notation. But that is what it means. The phi dx mu is phi comma mu. So you might often see me doing it even unintentionally. Okay.
So comma mu is the same as derivative with respect to
To x mu. Derivative is with respect to x mu.
x mu. Okay.
Right? There's no such thing as derivative with mu. Derivative is x mu. Remember x mu, x1, x2, x3, or x0. That's what it means. So phi comma 0 means the phi over dx.
Very nice shortcut.
Okay? What happens when we operate the dual vector, the gradient on a vector? Can do it, right? So operate the gradient d mu phi on a vector V. Like V is V mu. V mu.
You get a number.
Of course. So what is a number? It's quite easy, right? So V mu is dx mu over d lambda. We said that. Okay. So d mu phi dx mu over d lambda is a what? Let's use a chain rule, right? This is d phi dx mu over d lambda, so this is just d phi. Nice and easy after you spend 1 month breaking your teeth on it. Questions?
The only way how we can understand if this is a vector or dual vector is to check if the coordinates of it transforms as direct Lorentz transformation or inverse.
This is the definition, but you see it right away. Because if I write x mu, you know that I wrote a vector.
Yes.
And if I wrote omega mu, you know that I wrote a covector.
Yeah, I mean that sometimes it's
So you're
relatively easy, but for example with gradient, it's not obvious. You need to check before.
Yeah. You're dividing it by mu
Yes.
down, then it's not here that I put the, you divide by x mu, right? So x mu is upper, but then it's in the division, so d mu phi. Same here, phi comma mu, you see it's a lower index. It reminds you always that this is a covector. So I have d phi. Phi is a scalar function, right? So d phi over dx mu, x mu has an upper index, but it's in the denominator. Right? So I get the phi comma mu as a lower index. So it tells you that we are in
So after comma, you specify that this is lower in the
it's a lower index, of course. Yeah.
To understand why it's important to define the gradient as a dual vector.
So that's what it is. I just prove it to you. When I'm changing coordinates, the way the gradient transform is like a covector. It's not important to define, it just gets out of the definitions.
So, okay.
This is how we define a covector. Right? So everything that transforms as the opposite Lorentz transformation is a covector. That's exactly what the gradient does. Yes?
How can I describe quantities that don't fit those definitions, like angular momentum?
Wait. One step at a time. Right now we're defining vectors and covectors. More questions? So I can answer your question. What comes next? No. Of course. What did we say is a dual vector? Dual vector is a linear map, right, from vector belongs to TP to R. What do you think, Enzo?
From TP to TP star.
Let's try to generalize that. Not actually.
From one vector space to another. That's exactly it.
Just said.
It's not the general for.
So tensor T rank KL. Is a multilinear map of what? From a collection of k vectors and what? And dual vectors, right? Sorry, K dual vector, and L vectors to R. What does it mean, multilinear?
Linear both with respect to vectors
in every component separately. It's linear in every component. Okay. So what is a scalar?
Tensor of rank 0.
0, 0. A scalar, a tensor of rank 0, 0. What is a vector?
Tensor of rank
0,
Rank 0,
Which?
0, 1.
No.
1, 0.
Okay, dual vector, so 1, 0. And covector
0, 1.
is 0, 1. Is this something interesting?
Oh, wait.
This is the number of upper indices and this is the number of lower indices.
Ah.
The first one is dual vectors, right?
What?
The first is.
First is K. Tensor T of rank KL
Yes.
is a multilinear map from a collection of K dual vectors and L vectors to R.
So, my vector is.
Vector is rank 1, 0. So,
Because you're asking one good.
let's look at the transformation law of a tensor. Transformation law of a tensor. Right. How am I going to write a tensor? KL, rank KL.
T with K the lower index.
Opposite. So T U1, U2, UK, that's what it says. And then U1, U2, UL. No way basically. That's how I'm going to write it. And how is the transformation going to be? T U1 prime, U2 prime, UK prime, U1 prime, U2 prime, UL prime. How is that going to be? There's nothing too much you can do, to be honest. You don't need to be too confused. Lorentz transformation
With me, the
of
upper
every
index.
upper index separately, and inverse Lorentz transformation of every lower index separately. So T mu 1 prime, mu k prime, mu 1 and mu 1 prime is going to be equal to what? Lambda mu prime, mu 1 prime, mu 1, lambda mu 2 prime, mu 2, lambda mu k prime, mu k, and then lambda mu L mu 1 prime, mu 1, lambda mu 2 prime, mu 2, lambda mu L prime, mu L, times t u1 uk u1. So each component, each index is being transformed separately. Yeah? It looks ugly, but it's not that ugly. What else can you do? So, examples. So there's one tensor which you already know. Just didn't tell you it's a tensor. Please. What is that?
You mean tensor of rank 2, right?
There's nothing like rank 2. You have to specify two numbers.
So 2 and 0.
There is tensor rank 2, 0. There is a tensor rank 0, 2. So which tensor are you referring to?
No, I was asking if you're
What?
I was asking if you're talking about rank of more than one sigma. So
Of course. That's going to be limited. So, a tensor of rank 0, 2. What? You know it.
From mechanics.
By the way, did you encounter the concepts of tensors in any of your other courses? No.
a bit in the first quantum mechanical, the electromagnetic.
In E&M, you're supposed to see that. I know that for some reason you haven't been seeing. Sometimes you're supposed to see tensors in the E&M. Energy momentum tensor, stress energy tensor. Never mind. Now you know. A tensor of rank 0, 2 is a very important one. The metric. The metric tensor is a tensor of rank 0, 2, right? And how do I write it? Tell me, you knew. I have two lower indexes. Okay. So what does it mean that this metric, as being tensor, it acts on two vectors to produce a number, right? And in fact, this action is so important that it gets its own name. That's called inner product. So eta nu that as eta that's on V and W is the action of the metric tensor on two vectors. Eta acts on V and W is eta V nu, V nu, W nu. This we already decoded V dot W. There's also W dot V. And what's really written here?
Sum.
There's a sum. I can write it down as a minus V0 W0, right? Plus V1 W1 plus V2 W2 plus V3 W3, right? Remember how the metric tensor looks like. That is called, the inner product. Now, many concepts that you're familiar with, we're just copying them. For example, what do we say if the inner product between two vectors is 0?
They are
Orthogonal, right? So if eta equal to 0, then we say that V and W are orthogonal. Now the dot product, this is a scalar. So what happens to a scalar under Lorentz transformation? Nothing changed. It is not changed. And what does it mean? It means that if we select the basis vectors orthogonal to each other in one coordinate system, and then we transform them,
Still problem.
Yes.
they will still stay orthogonal. Okay. What is the inner product of a vector with itself?
No.
So the norm, right? So the inner product of a vector with itself is the norm. Norm of a vector v squared is eta mu v mu v mu, which we can also write it as v mu v nu v nu. Now we have a slightly different than what we're used to from Euclidean spaces. Eta mu nu v mu v nu can have three options. Can be smaller than 0, can be equal to 0, and it can be greater than 0. Norm of a vector can be smaller than 0. Yeah,
It's not positive defined. It was.
this is definition. So it can be smaller than 0. If it is smaller than 0, then we say about v mu that it is time-like. If it is greater than 0, then we say that v mu is space-like. And if it is equal to 0, it's a light-like or null vector. Now note that in Minkowski space, the vector can have a 0 norm without being 0 by itself. I'll show you that in a second. Speed of light. So, of course, the norm of a vector is a scalar, which means that it is Lorentz invariant, right? The norm of a vector v prime squared is eta mu prime prime v mu prime v mu prime. So I can write it, I can transform each vector by itself, so eta mu prime, and then this I can write down as lambda mu prime rho lambda prime sigma v rho v sigma. So this is exactly a transformation of eta. So this is eta rho sigma v rho v sigma, which is just v squared. And the same goes for any other scalar product between any two vectors. Yeah? Okay. So that's the metric tensor. There is another tensor of interest to us, which is the Kronecker delta. Now you've seen Kronecker delta, right? It's not something which is new. Another tensor, Kronecker delta. only tensor that I will write with indices one on top of the other because I cannot get two of these. What is rank of this tensor?
0, 0.
1, 1. This is a 1, 1 tensor, 1 upper, 1 lower. It's very simple. This is a 1, 1 tensor. And what are the components of this conical delta?
One if indices are the same.
Yep. 1 if mu is
Zero.
equal to nu, and 0
Otherwise.
if mu is. The definition of this tensor is very simple. Another tensor is the inverse metric. So I'll write this eta now is 2 upper indices.
It's,
Rank of this tensor
2, 0.
2, 0, right? 2, 0 tensor.
we use it for dual space. Right?
What?
We will use it for dual space.
Does not belong to TPC. It's got nothing to do with that space. It's an object by itself.
Yeah, but it acts.
It acts
on dual
on two dual vectors, yes. But since it's the inverse of the metric, then what's the definition of that? Eta nu eta nu sigma rho eta rho u eta and nu is equal to what?
Chronic delta with
The chronicle delta. Very good. With
lower
mu and rho. Right. Nu here is a dummy index. I sum over it. Right. U is upper index or lower index. I must always have the same number of upper indices and lower indices in both sides of the equation. Otherwise, I know that I'm doing something wrong. Clear. Okay. Now it's pretty straightforward to check how is if you write this inverse metric in terms of a matrix. What will be the components of the matrix? How will it look like?
Maybe
The
the
same,
same
minus
also.
one.
Exactly
only-
the same. Exactly the same as the metric. If I write eta mu nu, it's an upper index. Of course, that's only true in Minkowski space. When we get to more complicated spaces, then of course we're not going to have. This is always going to be true. This is the definition of the inverse metric. Then the last tensor that I want to introduce, you don't look happy. Don't look happy, I don't know why. Should be happy. Now you know what are tensors. I'm sure you've heard about them. Now for the first time somebody's actually telling you what they are exactly. And it's quite straightforward. There's nothing much more that you can do. That's the thing about it.
Can I ask you about the rank of tensor moment of inertia? It's
We'll
tensor
get
one.
to that. It's not exactly. We'll get to that. Actually, I'm not sure we'll get to that. Maybe I'll post it as forward. The last tensor that I want to speak about right now, we'll encounter more obviously. No, angular momentum is a bit more tricky. It's called the Levitz beta tensor. So this is a, do you know the rank of this tensor? It's a 0,4 tensor. it's defined by epsilon. That's where it's defined. So we've got epsilon. Mu rho sigma is a what? Is a +1 if mu rho sigma is even permutation of 0, 1, 2, 3. It's a -1 if this is an odd permutation, and 0 otherwise. You've seen this tensor before.
Yeah. Yeah.
But with free indexes.
Okay, so you're F4.
Okay.
That's not good.
Yeah.
So epsilon 1032 is equal to what?
One
Minus one.
Minus 1.
Y minus
1. It has
I got the
even
one.
number of permutations.
1. There's one permutation here, one permutation. Okay. What can we do with tensors? We can do many things. We're going slow, one step at a time. So the next step is manipulating tensors. So, given a tensor, what can we do with a tensor? So we can create other tensors. One thing which we can do is to raise and lower indexes. How do we do that? How can we raise an index or lower an index? By the metric. And the inverse metric. And the metric and the inverse can be used same as the example for the norm mixing. So the metric using the metric and the inverse metric. So let's say we have a tensor T alpha beta gamma delta. Right? I want to make a new tensor T alpha beta mu delta is equal to what? I'm given this tensor. I want to produce a new tensor.
So lambda with mu lowering.
My lambda, where is lambda?
Eta.
Eta.
With mu lowering. No, it's beta and the lowering goes.
Why do you touch beta? What do I do?
Gamma upper index and mu upper index.
Right,
Gamma.
very good. Mu gamma.
Yes.
Okay. Gamma becomes gamma index, replaced by mu. I have a new. Let's say I want to have T mu beta gamma delta is equal to what?
Eta.
Somebody else now. You got the idea. Somebody else? What do you do?
Mu alpha
alpha below, mu alpha, right. Mu alpha. Note that I don't touch the other indexes. They stay the same, and they stay where they are. I don't switch the order. It's important. I only raise and lower indexes, that's all. Not moving them. That's I'm not allowed to do. T whatever. New rho sigma. Now help me. What do I get? What do I do to get that? First index.
U.
Eta. What will be in the first index?
U alpha.
Mu alpha.
Lower.
Lower or upper?
Lower.
Lower. Mu alpha. Second index.
Mu rho lower.
No, sigma gamma alpha.
This is a beta.
Oh, it's a beta, so
Ah,
mu
it's a
beta
beta.
lower.
Yeah? What?
Mu beta lower.
Mu beta. Somebody else? Third index.
Rho gamma upper.
Rho gamma upper. And last index.
Delta upper and
Sigma delta.
sigma delta.
Sigma delta. It's actually very simple, right? You can only get them up or down. That's what you can do. Don't move them sides. That's all you can do. Okay, so position stays the same. Also, again, clearly, the indices and their location, upper or lower, are the same in both sides. And when we have a dummy index, which one here is a dummy index? Alpha, right? So what we're really doing here, we're summing over it. Okay, don't forget that. Normally it's not a big deal because the eta, which gives mostly zeros, but that's what we really do. Okay. That means that the metric and the inverse metric can be used to connect vectors and dual vectors. You already said that, right? So given a vector, v mu, how do I make a dual vector?
Is a lower.
Dual vector is a lower index.
So eta.
Using the metric. Right? Of course, the inverse. If I'm giving a dual vector, omega, we can use here. Yeah. How can I make a vector?
You need it upper.
Eta mu. So the metric and the inverse metric really gives us a way of connecting vectors and dual vectors. And again, that explains again why you could never tell in Euclidean space that a gradient is not a vector but a dual vector. Because in Euclidean space the metric is simply 1, 1, 1. So you don't care. Vector and dual vector looks exactly the same. Only in three-dimensional space, which we're no longer living in. Yeah, there's something. There's some. Okay, I put a note for myself here. That in principle, that's for you to know. In principle, the concepts of vectors and tensors is basic one, namely you don't really need a metric. They can still exist there without a metric. We will not touch that not in this course, and we'll always have a metric in this course, so you don't need to worry about it. But as conceptually, these objects exist. The alarm. I said two important things. I said one, okay, so the metric and the inverse metric Right? So we said that the metric and the inverse metric can be used to raise and lower indices for vectors, to transform them from vectors to covectors and vice versa. I said that's quite crucial, that it's not crucial for this course, it's just crucial for understanding in general, that the vectors and covectors are the structure that appear on the manifold without the need for a metric. Okay? There are very strange manifolds, which we will not really discuss here. You know the Mobius strip? I think it's a manifold, it's a non-orientable manifold. There are various strange manifolds that are there. That's for a more advanced course. For here, it's just, don't need to worry about it. So just that you know that vectors and covectors and tensors, they exist as objects on manifold, regardless of the existence of a metric. You can think of them still without. Okay, so that's one thing which we said we can do with vectors, is to raise and lower indices. Another operation which we can do, there are several operations, but we'll slowly get there. There's no point in doing everything. So the second operation that we can do with vectors is called contraction. What is a contraction? Contraction is an operation that takes a KL tensor and turned it into a K minus 1 L minus 1 tensor. How? How do we do that? We simply sum over one lower index and one upper index. Okay. Again, I mean, it's quite simple, right? This is a number of upper indexes and number of lower indexes. So there's nothing. There's no alternatives, right? So, for example, if I have a tensor which is T, where do I write? Mu, nu, rho, sigma, nu, right? I can sum over the second and fifth index to write the new tensors S, mu, rho, sigma. Okay? So I always sum over one upper and one lower index. There's really a summation here. And that's completely legitimate. Very important, right? You can only sum on one upper and one lower index. You're not allowed to sum on two upper indexes or two lower indexes. This is illegal. Right? Only one upper and one lower. That's the first thing to remember. The second thing to remember, the order of the other indices do not change. Right? Every index has its own location. You're not touching them. You cannot move indices back and forth. That is illegal.
I can choose which ones to sum by.
Sorry?
I can choose which ones to sum by, right?
Yeah.
Because
It's fine.
I can change it however I want.
Yes. So the order of indices matter. So, for example, T, mu, nu, rho, sigma, nu is not the same as T, mu, rho, nu, sigma, nu. They are not the same tensors.
Okay, but if we change lower index, it will be the same.
If we change what?
Lower indexes,
What do you mean?
like sigma and.
Here I'm summing. Here we are summing over the second and fifth,
Yeah.
and here we're summing over the third and fifth. So we get the tensor here, and we get the tensor here, but they're not going to be the same tensors.
I mean, we keep all of upper indexes the same,
Yes.
but change sigma and nu.
What do you mean?
The result will be the same.
What? If you do like mu sigma?
Yeah.
No, of course not. It will be a different tensor. You can write down as that, and then you have a different tensor. Whatever W is T mu nu rho mu sigma. That's a different tensor, and W is not the same as S, because here you sum over the second and fifth, and here you sum over the second and fourth. So you get tensors. This is tensor. W, mu, rho, sigma. They have the same number of indices, but they are not the same tensors. For example, you can have a v mu and x mu. Those are vectors, but they're not the same vectors. They belong to the same vectorial space, but they're not the same objects. Okay. Okay. That's now we're gonna. So far, everything we said was pretty much mathematics. Now I'm going to leave the maths behind, and we're going to do physics. So this course is sort of the edge between math and physics. And the nice thing, after you fully understand all this math, I'm sure you fully understand everything I said now. But if not, you're supposed to stop me and ask a question. If you don't do it, then I know that you fully understand. It's your responsibility. And you'll get homework. Okay? And now we can see how that translates to the physics. The physics, you're going to see, we're going to get it for nothing, for free. I'm going to do the entire thing you learn in special relativity. I can do it in half an hour. Since we're close to the end, then I'll just start now and finish that. First half hour next. So we work very hard on doing the math, but now the physics will come out as for nothing. So, special relativistic kinematics. For velocity, acceleration, and for force. Okay, so now we're going to speak about physics. Now we start by noticing that we have a problem. What's the problem? In the classical mechanics that we speak, right, there is a standard way in which we're used to think of things and present things, right? We're saying that an object is at some location at some time, and we're looking at how this location changes over time. So we said, okay, xi is a function of t, right? We have an object, and the object moves, but here it doesn't make sense to do that, because t is a coordinate by itself. So we cannot use that here. So we need to specify something else. What do we do? How do we solve this one? What? Right. So we get to tau in a second. What we do, the easiest way to think is to think of a moving particle in space in terms of its space-time location. In special relativity, relativity in general, we think of the space time location of the particle. This is in Newtonian mechanics. Now xi. What does it mean? I draw a curve. I basically take all the space coordinates in the x direction, so I can easily draw them. So this is x and this is c. And the location of a particle is drawn by a curve in that. course, time always progresses, so we're always going upward in that curve. If you go down, that means time goes back. So space-time location. The space-time location of a particle describes a curve this curve has a name. You may know the name. Word line, which is called word line. Remember I told you this earlier. So I can specify my location, right, by some parameter along the word line. This is my word line. There is some parameter which I can choose, number. You rightfully said I can choose any parameter that I want, but there is one parameter which is easier than others to choose, which is proper time. So time is proper time. Just before I get there, what will be the word line of a photon look like in that curve?
Straight line.
Straight line? Which?
Oh,
At 45 degrees, right? So if there is a photon, actually this is a wrong word line. If there is a photon that is emitted here, it can go, it will always go in 45 degrees. Right? Always. Right? Let's run it back. Let's forget about that. 3D. I realize that my word line is what type of vector it is? It's a time-like. The photon is always a photon. It goes always along null vectors. It's always 45 degrees. Can I do something like that in my word line? Why not?
faster than the speed of light.
Yeah. If I want to do that, I need to travel faster. So I'm always confined to an angle which is less than 45 degrees in this schematic view of my word line. Right? So the description of the motion, or describing a motion, description of the motion, is basically specifying x mu as x mu of c lambda, whatever you want, but in reality it would be of tau. Given that, so x mu is my location. How do I define my velocity, my forward velocity? Very simple. Right? So my forward velocity u mu is a derivative with respect to tau. Tau is a scalar, I got no problem, I can take it. Full derivative. Very simple. Like any other vector, u mu, the forward velocity, is defined at a given point in space-time. Okay, that's what we said earlier. Now remember the proper time we had d tau. Now that delta tau squared, we had it as minus 1 over c squared at the mu dx mu dx mu. Right? So d tau is d squared minus c squared. Square root. Write as dt square root of 1 minus dx over dt squared over c squared. Dt square root of 1 minus beta squared. Ah, got that. Now, after I define the form velocity, what is u0? D. What is x0? Ct over d tau. Tau is right here. Square root of 1 minus beta squared dt. C over square root of 1 minus beta squared. What is square root of 1 minus beta squared?
Gamma.
Gamma. What is ui? dx9 over square root of 1 minus beta squared dt or beta squared dx9 dt, which is gamma times vi, or I can write as gamma times beta I c.
Why the u0 can be greater than c?
It's a problem. Why do you have any problems?
Because it's
Gamma is always
component
greater
of
than 1.
velocity.
It's a
Velocity can
4
be
velocity. It's not a 3 velocity. It's a 4 velocity. That's the definition of 4 velocity. It's not the same 3 velocity that you're used to.
in principle it can be greater than c.
It's always rated than c, because gamma, when you're moving, gamma is always rated 1.
Yes. Greater or equal.
Yeah. Most textbooks you get c equal to 1 at this stage. You're still keeping the c so that you make sure. Try to help you. Why is it a problem? What is the norm of the 4 velocity? Let's see. Norm of u u squared is u mu This is eta mu mu, which is eta mu dx mu over tau dx mu over tau. Now I'm doing something which is semi-legal. I'll just write it as eta mu dx mu over d tau squared. Tau squared, should be like that. What is eta mu dx mu?
Yes.
Yeah. So this is c squared minus c squared d tau squared. So we end up with this is minus c squared. So first this is constant, right? We said that the normal vector is constant. And it's a negative. Really it's a negative 1, but it takes it to 1. Something like that. Okay.
Why we call it timeline? Then the norm is
Because it's because I'm think of it like that. I'm traveling faster in time than in space, in a way. In that org line, CTX, which is limited by this 45 degrees, I'm always confined here. So my time always goes up in this direction. I always go up.
okay. And then how space-like projectors?
as you rightfully said, this represents particles that move faster than light.
If,
Yeah.
if two events are time-like, does that mean that the order of the events will be the same in all frequencies?
That means that they will be causally connected, which means that one event could affect what happens in the second event. It's not necessarily, actually yes, it does mean that we can change the order. If they are space-like, they mean that they are not causally connected, which means there is no way that anything that happens, that I will know that anything that happens here will affect what happens in that. And I think you mentioned it, or somebody else mentioned it. That is one of the conceptual problems that lead in quantum mechanics, because in quantum mechanics you don't have that. That's one of the conceptual issues that lead to the formalism of quantum field theory. Exactly in order to avoid that, so to avoid a situation where you have events that occur so far away from each other that they don't affect each other. In quantum mechanics you can have it, but obviously we don't see that in reality. Okay, I think this is a good place to stop because we're already over time, but that's not our fault because there was alarm plus a few minutes which we missed at the beginning. Any questions? No? Okay, I'm shortly going. Guys, again, I guess you're more and more seeing what I refer you to, so that it's very, very, very easy to get most of this course. So, and we're just very strong. So, but it's okay. I mean, just make sure that you're with me. It's your responsibility. That's what I want to say. It's not that it's going to be very difficult. I'm not trying to scare you. We'll go through it and we'll make sure that you understand everything. It's fine. But it's your responsibility that if something you don't understand, then you go and raise a flag and say, okay, I understand. All right? Okay. I'll see you on Sunday, 10 a.m.